and I am in the software for more than almost 2 decades now. When I joined ThoughtWorks, I was not a developer, but now I am. So I joined as a business analyst, and ThoughtWorks allows you to basically switch things if they work out. And I became developer because I was very passionate about functional programming in Scala at that time, 9 years ago. I was evangelizing, and yeah, I think that's the reason I'm a dev today. And I'm for last 4 years, I'm working on this cool project I'm going to talk about today. So that's in very brief about me. Over to you, Purva.
Yeah, so thank you, Mushtaq, and hello everyone. I am Purva Gokhale. I am also working out of Pune office, and I am working with ThoughtWorks for more than 5 years now. So, like during the journey, I have worked on various domains and various tech stack, and I would say I'm very fortunate to get an opportunity to work on TMT, 30-meter telescope project, and we'll be sharing about TMT today. Yeah, over to you, Pritam.
Yeah.
Yeah, hi everyone. I am Pritam. I have joined ThoughtWorks 4 years back, and I have joined TMT since the beginning. And as same like Mushtaq, I also joined as a QA, and within the TMT, I switched my role to dev, and currently working on Scala. I'm passionate about programming. Yeah.
Thank you. Hello, everybody. I'm Chaya. I am from the Pune office, and if few of them are from the last session, they may know me. I am delivery partner for engineering for research and also project manager for the 30-meter telescope. So 30-meter telescope happens to be the flagship project for engineering for research. And once this mega structure is going to be constructed, it's going to be a marvel to watch. But then such engineering expeditions also require great functional and operation challenges that need to be addressed. And I think TMT project software development from ThoughtWorks is addressing one of those challenges. So let's hear from the team, and over to you, Purva.
Yeah. Hello everyone, and myself Purva Gokhale. So today, me and my colleague Mushtaq, so we will be speaking about 30-meter telescope. And 30-meter telescope is one of the project of E4R service line, Engineering for Research service line. And in TMT, we are collaborating with IIA, which is Indian Institute of Astrophysics, Bangalore, and TMT Project Office. Yeah. So, like 30-meter telescope, TMT. So it's going to be one of world's largest optical telescope once it is operational in 2030. So 2030 is the current planned date when TMT will be seeing its first light, and the first observation will be done in the 2030. So it's like pretty long running project, almost 10 years from now it will be operating. So when I say 30-meter telescope, so 30-meter is the diameter of the primary mirror for the telescope. And it's nearly impossible to have such big giant mirror. So this 30-meter giant mirror, it's made up of 492 hexagonal segments of glass. They will be pieced together to form this giant primary mirror. If we compare TMT with existing visible light telescopes, then it's like 3 times wider and 9 times more area. It's going to be a huge structure. And with this giant primary mirror, the image which will be captured by TMT will be 12 times sharper than that of Hubble Space Telescope. So there are like multiple countries which are collaborating for TMT. So the location for the 30-meter telescope is going to be Mauna Kea, which is in Hawaii. And then these 5 countries like USA, Canada, Japan, China, and India, these 5 countries are collaborating for different work for TMT. And India is primarily focusing on software part, and that's where ThoughtWorks collaboration come into picture. Yeah. So as I spoke, right, that TMT is going to be a really huge telescope. and this is classified as a next generation telescope. And along with TMT, there are other two telescopes for which the work is in progress. So the first one, which you see over here, is the ELT. This is the extremely large telescope, and this is going to be built by the European Union. The diameter size for the ELT is going to be 39 meters, and ELT is going to be situated at Chile. So this is TMT, the 30-meter diameter telescope, and the location is Hawaii. The third one is the GMT. This is the Giant Magellan Telescope. The diameter for the Giant Magellan Telescope is 24.5 meters, and it's also going to be situated in Chile. So both of these telescopes, like ELT and GMT, they will be covering, or they will be in the area southern hemisphere, and TMT is in will be situated in Hawaii, which is the northern hemisphere. So resolution that these telescopes will be offering is also different. Like ELT is offering 15 times sharper image than that of Hubble telescope. TMT is offering 12 times sharper, and GMT is going to be 10 times sharper than that of Hubble Space Telescope. So if we look at the mirrors for these telescopes, so this is how the mirror will look like for ELT, which is the European Extremely Large Telescope. So this is also like hexagonal glasses pieced together form a giant mirror for the telescope. This is how the mirror structure for TMT is going to look like. It's like multiple hexagonal glasses pieced together to form that giant big mirror. The mirror for GMT looks slightly different. It's like seven giant mirrors forming the 24.5 diameter mirror for GMT. So why are we calling these as a next generation telescope? And it's because of its huge mirror structure. So if we see, these are like the existing telescopes, which are actually currently present, visible light telescopes in the world. And this is the size for these existing telescopes. And if you really look at the size for these extremely large telescopes, like next generation, all three of them, they are like really, really big as compared to them, as compared to existing visible light telescopes. Yeah. So like what these next generation telescopes or the TMT, that what they will help us to explore. So they are really going to enable astronomers to answer the open outstanding questions in astronomy, like really the unknown part that will be like explored with the help of TMT. TMT will allow astronomers to look at or study the black holes, which are at a center of distant galaxies, and also the black hole which is at center of our own Milky Way. Then it will also enable the scientists to study the mysterious period in the life of universe when the first planet and first stars were formed. So this is like very so TMT and all the three, I would say it's going to be a milestone, and it will really going to enable astronomers, and we will be able to answer some of these questions. So that's how important these three telescopes will be in the astronomy domain. So I talked about the resolution that TMT will be providing. So this is the image. This is taken by Hubble Space Telescope, and it's the image of Hubble Deep Field. And the next image, this image is also of Hubble Deep Field, but it's taken with TMT. It's like the simulated image, but this is the kind of clarity, like 12 times sharp image. So this is the kind of clarity that is expected out of TMT. So just to speak about the key dimensions of this huge structure. So we spoke that the diameter for the primary mirror of telescope is going to be 30 meters, and it's going to be 56 meters high. So it's really going to be a huge structure. You can imagine it as a 15-story building, huge structure of TMT. And these are some of the key dimensions of the telescope. So just to get an idea, I'll be playing this video. So you can see that this is the TMT dome. And you can see that the aperture is opening. Here is the primary mirror, which I was talking about. It's like multiple hexagonal segments. They are pieced together. And there will be multiple mirrors in the TMT. So this is the tertiary mirror. So 3 mirrors will be actually collaborating and the image will be extracted out. So this is how huge the structure is going to be. You can see people standing over here, actually the operators and TMT staff. So this is the telescope summit. Yeah. So you can see that this laser beam coming out of telescope. So TMT is operating or working on the adaptive optics technology. So what they actually will be doing is this is the laser beam which will be thrown in the sky and artificial star will be formed. And as this is the artificial star, they will exactly know the parameters or the location and all other parameters for this artificial star. And then they will actually observe this star using TMT. And then what will happen is like they'll calculate the error margin between the expected and the actual image, and that's how the error correction is going to be done. So this is to just get an idea about the error margin or the delta between these two images due to atmospheric disturbance. And then this error margin, this correction will be done for all the observation. Then that's how the adaptive optics technology will be used to capture the images which are like really precise. Yeah, so this shows the primary mirror for the telescope, and this is the basketball court. So you can just imagine like how huge this mirror will be. Yeah. So this is also an illustrative video. It shows that light is reflected on the primary mirror, and that's it's getting reflected on a secondary mirror. So this is the secondary mirror, and here is the tertiary mirror. So tertiary mirror is actually directing this light to different instruments, and these instruments are responsible for different tasks. Like some of the instruments are responsible for adaptive optics. Some of the instruments are responsible for infrared imager. Some are wide field spectrometer. So this tertiary mirror is actually directing this light to different instruments, and these different instruments will be working on different wavelength of the spectrum. So not necessarily that every instrument will be in use at same time. So depending on what kind of observation is going on or what is the observing mode, according to that, different instruments will be capturing the light, and actual image or actual data will be extracted out of those. So it's like it's a mega structure, as Chaya said. And once operational, TMT is going to be operational for 50 long years after 2030. So with the time, like technology will advance, and if there is some advancement in technology, so those kind of instruments will also fit in there. So it's like a plug-in kind of thing, and that's how they are claiming that they will be scaling with the advancement of technology. Yeah. So as you have said, as you have seen, like it's really big structure, and there will be multiple hardware components, and also along with the hardware components, software components will be there, and that's where actually the ThoughtWorks contribution comes into picture. So what we have contributed so far is these three different modules. So CSW is the common software or the platform services. So there will be like number of hardware components which are distributed in nature, and these components will need to communicate with each other. So for that, we have built up a service discovery mechanism. Also, these components will sending commands and publishing data, which might be a telemetry data or science data. So they will be publishing this data continuously, and the ecosystem for these hardware and software components to work, a common platform is provided by the CSW. Then the next one is the ESW. This is the executive software or the telescope operations. So this telescope components, they require a synchronization for the tasks such as mirror rotation or filter selection. So all this synchronization, then monitoring and control of observation, executive software, and it's the ongoing work. Uh, the next one is the DMS. So DMS is the data management system. So this is the telemetry and science data. So what we are doing as a part of DMS is actually we are working on two services, metadata collection service and the archival service. So when these components, they will be collaborating and they will be communicating. So they will be publishing a lot of data, like what are the temperature values, moisture values, and so on. So data management system is focusing on capturing that data as a snapshot and also archiving that data for future analysis. So all the work that we are doing as a part of TMT, like CSW, ESW, and DMS, it's all open source. And I'll be sharing, I'll be showing you the GitHub projects where we are actually working. Yeah. So I'll be talking about the architecture of TMT. So it's a layered architecture. So layer 0 is the observatory hardware. So like TMT structure is going to be such a use, like there will be n number of hardware components, and these components will be responsible for different types of work. Some of the components responsible for controlling the telescope, like mirror rotation. Some of the components are responsible for infrared imaging, and some of the components responsible for adaptive optics. And all these components will be having a custom protocol at their hardware level. So this is like the layer 0 of the observatory hardware. The layer above this is the hardware control layer, and you can imagine these as a device drivers. So for each hardware component, there will be one HCD or hardware control daemon instance running. So these HCDs will actually understand how to communicate to the downstream hardware. And this is the actual first software layer. And this is when the ThoughtWorks contribution starts. So all the layers above the HCD layer, they will be communicating in the common protocol. And this common protocol is provided as a part of CSW, or the platform service layer. The layer above this is the assembly layer. So like there will be multiple hardware components responsible for controlling telescope. And all these components, they form a logical group, and the logical group we call assembly. So this assemblies will be responsible for a bunch of hardware control daemons and actual observatory hardware, which are responsible for a logical work. So that is the assembly layer, and both of these layers we have provided as a part of CSW. The next layer is the sequencing layer, and we have talked briefly about the ESW, or the telescope operations, and that's where this layer comes into picture. So just to give an example, like how TMT will actually work. So scientists will be submitting their proposals, and these proposals will be selected based on the conditions and requirements. And once the proposal is selected, that proposal will be converted into sequence of steps, and these sequence of steps will be sent to the master sequencer, and master sequencer will actually know what to do when particular step is received, and it will flow that, or it will send that step to downstream sequencers, and till the observatory hardware, and the actual action will be taken at the observatory hardware layer. So this is how the actual observation is going to flow from sequencer till the downstream hardware. So this is the sequencing layer, which is provided as or delivered as a part of ESW module. On top of this sequencing layer, there is the application layer. So application layer is for the telescope operators. So telescope operators will actually be sending sequence to this OCS master sequencer, and they will be managing the observations. Like at one point of time, there might be concurrent observations going on. Like one observation is actually observing a portion of sky, and another is might be the calibration of some instrument which is not needed at that point of time. So managing these concurrent observations, managing the infrastructure and the resources for the telescope is where the application layers comes into picture. Yeah, so we spoke briefly about these three layers like CSW, ESW, and TMS. So this is a bit in detail, like what we have actually provided as a part of the platform service. So like I said, the different components will be there and they are distributed in nature. So whenever a telescope, one component will need to send a command or will need to communicate to other component, it will need to locate it. And also whenever a new component comes into picture, the new component will register itself, so it will become a discoverable. So the service discovery mechanism and what we call it as a location service is what we have provided as a part of CSW. And this location service is like it's very interesting. It's backed up by Akka CRDT, and Mushtaq will be talking about location service later in time. So apart from location service, we have also provided logging service. So logging service is mainly for these different components will be logging what is their state and what are the values of certain parameters. So for centralized logging, we have provided logging service. So command service is the common protocol which I was talking about. Like multiple components, hardware components are communicating with different protocols, but command service provides a common protocol layer and it's backed up by Akka. Uh, the layer above HCDs, they use this command service to communicate with each other. Another interesting part which we have worked as part of CSW is the event service. So event service is required when these multiple components will be publishing a lot of data, telemetry data as well as science data. And there are very challenging requirements over there as telescope systems need to act faster when they receive any kind of event. So about these challenging requirements and how did we achieve those also will be covering next in the later part of the talk. Alarm service also be provided as a part of CSW. So alarm service is mainly for like components will be publishing their states, like they are in healthy state or critical state. And if they're in critical state, the operators will be taking some actions. So for that, alarm service is provided. Database service for storing some kind of configurations and some any kind of data. So that for that we have provided database service. Auth is for like various roles will have different types of permissions. Some operators will be responsible for managing infrastructure. Some are responsible for particular sequencers. So for the auth purpose, we have provided authentication and authorization service. The next interesting service which we have worked as part of CSW is the time service. So time service is like telescope operations will need very precise scheduling of some tasks. And for that, we have implemented time service using PTP, like we have implemented precision time protocol. And that's what the time service module is for the CSW platform. Another service which we have worked upon is the config service. So config service is nothing but it's for storing various types of configurations. So these components, they will have multiple configurations, like on which machine, which component is running. And this config service is backed up by version control. So these are the services which we have built up on as a part of CSW, the common software or the platform services. Yeah, so the next bigger chunk of work which we have delivered and also we are working on currently is the ESW, and this is to smooth out the telescope operations. So I spoke little bit about sequencer. Like sequencer is like the proposal, scientist proposal is converted into sequence of steps. And the job of sequencer is to execute this step one by one. So this is the framework part that we have provided. And what to do when particular step is received. So that logic is in the script. And these scripts are written by the domain experts. And these domain experts, it's like interesting persona. They know the telescope operations, but they are non-programmers. So for them, we have provided a scripting DSL. This is the domain specific language embedded DSL that we have provided. And this also will be covering in the next part of talk. Then there is a sequence manager module, which we have provided as a ESW. So sequence manager is mainly responsible for managing the observations, the concurrent observations, configuring those observations, also looking at the telescope resources and managing the infrastructure for Telescope. So for that, we have provided this software component called Sequence Manager. API gateway. So API gateway is the HTTP face for all the components. So if any outside or public engineering UI, they want to talk to these components, they'll be going via HTTP gateway. And this is where the auth layer for the security purpose will also sit. Agent service is also very interesting. The requirement was that one should be able to start any component, any TMT component on any machine remotely. And for that, we have developed the agent service. Then this ESW also comprises of engineering UI. And this engineering UI will be used by Telescope operators. And they will actually use this engineering UI to send a sequence to sequencer, and they'll be looking at the state of each sequencer and the state of observation. So for that, it will be like a very complex UI, Telescope UI, which we are building. And we are using all the modern web technologies to build this engineering UI. There are very different and interesting tech choices over here. And Mushtaq will be talking about the engineering UI tech choices also in the section of tech highlights. And for building this engineering UI, and also there will be many other UI applications which will be actually responsible for monitoring the telescope observations. So for all those applications, we have exposed the libraries, the TypeScript libraries, which will actually enable the UI developers to write their applications. So this is the ESW part. Then the DMS. DMS is also a bigger chunk of work which we are working on, and the DMS is in the prototype phase. So what we are building in the DMS prototype phase is these two services. One is the metadata collection service, and another one is the telemetry archival. So metadata collection service, this is actually responsible for taking a snapshot of all the events that Telescope components will be publishing. And these events will be captured in the snapshot when particular trigger is happening. Like maybe the triggers may be like exposure has started or shutter is open. So whenever any kind of trigger is there, the metadata collection service will actually take a snapshot, and it will attach FITS header to this snapshot. FITS is the standard in astronomy. So it will attach the FITS header to the event snapshot. And there are some performance requirements here which we were able to achieve. And these metadata collection service and telemetry archival, both of them are dependent, or they are built on top of event service, which we provided as a part of CSW. Then another service is the telemetry archival. So the telemetry archival is nothing but these events that various components are publishing. They will need to be stored for 50 long years for future analysis, or maybe troubleshooting, or diagnosis. So for all that, this huge amount of data that Telescope will be generating per day, per observation, that needs to be stored. And for that, the telemetry archival service is what we are building. This is also very interesting part, and we are going to talk about it. So these are like the three modules where ThoughtWorks have contributed so far. And we might get involved in more parts of the system later in time. So this is like Telescope system is going to be very, very, very complex. Some of the systems will be responsible for processing the data that Telescope is generating. Some of the systems responsible for controlling the telescope. So this is like in big picture, this all are the systems that Telescope will comprise of. And this is the highlighted part where ThoughtWorks is currently contributing. So this green line is the CSW module, which we talked about. This is the ESW part, executive software, or the telescope operations, sequencer part. And the third one is the DMS part. So this is in the prototype phase, and we are working on it. So these are the current areas where ThoughtWorks is involved in, and we are expecting that we will get involved in more and more areas. So these are the big picture, and I'll actually be showing you the repository. So this is the TMT GitHub organization. It's all open source, and you can see the projects over here. So CSW, the module which we talked about. So this is the CSW module which we have worked upon. And we have also done, because it's very long running project, so we have also done the extensive documentation. So this is the tmt.org. This is the site, the official TMT site, and here you can get all the information like regarding adaptive optics or the timeline where it is going to be built and all. Yeah, so this is the part which I was talking about, like the extensive documentation which our team has provided. So telescope will need to be maintained for longer duration, like 50 years, and for the maintainers and also for the users of the telescope, we have done this extensive kind of documentation. So this is the CSW repository. Along with CSW, you can find here like ESW also, the ESW module, the engineering UI, which is currently in progress, the TypeScript library, then ESW, the entire work package, then DMS. DMS is in the prototype phase, but we are like concretely building and spiking out different technologies, and all the code is open source, and you can find it here. Yeah. So So this is about like how what ThoughtWorks has contributed in terms of software so far. And as I said, it's like very unique and different project, and we have been solving many challenges throughout the journey. And Mushtaq will be talking about these tech highlights. But before that, does anyone have any questions? Like, we'll be happy to answer if you have any questions so far.
Yeah, Purva, I do see some questions on the chat. We can address them now. We can address them in the end. It's up to us. I think one of them was about why Scala. Pritam answered that. I can also take it, or go ahead. I mean,
sure, if you want, we can go through the questions. As you said, they've been already quite thoroughly answered in the chat, but there is the question about Scala, and there's another one about interconnected services and devices. Did you want to address this? Yeah.
The second one, I'm not sure, but let me talk about the Scala, because that is also one thing Purva wanted me to say about how we got involved in the project. I was a Scala enthusiast, and I was introducing myself that was the reason I became developer, and I was working on projects in Scala as a technology business project. And at the same time, TMT is going on for already many years. I mean, we got involved 4 years ago, but it was in design for before that. And the architect of the current TMT project, he is into this telescope domain for multiple decades now. He's been working with all the latest telescopes, optical telescopes in the past. And he has moved from one technology to the other. I mean, he started with C++ and then Java, and then his community that he came from, they have moved into Scala because of functional programming. And also because a large part of this control system and the user interfaces and other application software, they don't have this need to be written in C, and they don't require that level of control, real-time control, which C or Rust can provide. So he was already onto thinking that we should do it in Scala, and India is a partner who is going to do the software. So he was looking for a vendor in India who will be able to deal with this. And we were hosting an event in Scala and showcasing our expertise, and that's how we met, and that's how this engagement started. So I don't think it was like decided that, okay, let's do a study and find out which is the best suited language. I think we were enthusiasts, we were experts in Scala, and the architect had already decided based on the merits that, okay, it's a feasible language to choose, and that's how we selected that. Is that the other one I haven't seen, so maybe we can we can take it later. But go ahead. If there is anything else for Purva, go ahead, please.
There's one question that just came in that maybe would be related. How did the architecture evolve over time? What were the first components to be built?
Yeah, so CSW was the like first module which we started with. And the first, like it's in the TMT project office, it follows the waterfall process. So it's like it's like bottom up, like the FCD layer and the assembly layer. Those were like the first components which we have built, and which we are going on the top. Like after assemblies and FCDs, we have delivered the sequencer layer, and now currently we are working on the UI applications. So that's how it is, and we are incorporating like ThoughtWorks being agile enthusiast, we are incorporating the agile in the waterfallish model itself. Like in their design phase, we are doing inceptions and we are doing the 2 week iterations. And actually, at the end of every iteration, though it's a prototype, though it's a design phase, we carve out something to actually showcase our stakeholders. We have calls twice a week, and we showcase them and get their feedback, and iteratively we develop some of the technologies, some of the components, and improve it. Mushtaq, would you like to add anything?
Yeah, I think there were some decisions because, as Purva said, they follow waterfall, and that's not because of software, right? I mean, software is the smallest part of the telescope, so they do planning for the rest of, like, right from the building construction to mirrors to hardware and also software, and they do it in their own way, and we have to fit in our agile thinking, iterative thinking. But yes, there is scope for software to evolve. I mean, at times, the design team or the architect, they end up committing to some approach, which we realize that is not going to work later on. And then we have a way to change that. One of the things I'm going to speak next about service discovery, the architect had a different idea how to do it. But once we started working on it, we changed it, and he got it approved, and that is in place. So yeah, even though it is waterfallish, there is a scope for evolving. And what are the first components to be built? Well, some of them will be built by us. I mean, we are building a lot of CLI, command line applications for utilities, basically consuming our own libraries and services. We are also building, as Purva pointed out, the engineering UI, which is going to control the operations of the telescope. And some of the other teams who are going to consume, one of them is based out of Canada. The Iris is the name of the device they are building, which will be the first camera that will be operational. They are consuming our layers and building drivers around that. Yeah. Can you see it now?
Yes.
Okay, good. So I'm going to talk of some things that we feel are important and interesting, and we have done it differently, right? So they are like a mix. There's not a coherent story here. Now I have picked up interesting bits of technology, and maybe it will be a little bit deep dive into some of them, a bit different than what Purva spoke about. So let's talk about the first one, which is the CRDTs for service discovery and what it is. So, okay, sorry. So CRDT is being used for this component, the location service, as Purva pointed out, and it is part of the platform, or CSW, that is our internal term for that. And I'm going to do some translation in the business terminology. The terminology used by the telescope is different, and we have to continuously map it. So I do that attempt when I talk about the services. So this is the location service is nothing but the service discovery mechanism in terms of business services. And it is required for the same reason business services will require it, because in a assuming a microservices application, you will have to discover a service by name to be able to send a message or receive some information. Similarly, each of the device driver, and there are going to be dozens of them basically, right, in the telescope, they need to reach out to each other using name and then exchange commands and messages. So to be able to do that, they need a mechanism, and we have done it differently. So like any other service discovery mechanism, we had similar requirements that we should have minimal configuration, should be highly available, because there's a central service. Every one component will use it, and it will be used very often, maybe every second by some of the components. Should be fault tolerant. The watches, which means that I should be able to track a location or a address or a name basically, and then see if the address is updating against that name, because a device can go up and down, and I should be able to know the latest thing. And yeah, I should be able to support not only just the HTTP, but also the actor references, which are one of the main mechanism of communicating within TMT. And we have option of using Consul or etcd or Zookeeper, which are similar systems used otherwise, but they will require us to set up a cluster just to have all this property, a separate cluster. And we, as you can see, that our software is going to get complex over a period of time. So we are trying to minimize the extra systems if we can. We were already dealing with Akka cluster because of the other TMT requirements, and we realized that Akka cluster offers a library called CRDT, which allows distributed data structures, which can be used for working with service discovery mechanism. So I'll in brief tell what is CRDT. CRDTs are conflict-free replicated data types. In short, they're data types which will work in a distributed fashion, allow concurrent updates, and eventually they will become consistent. They will have the same information, but while doing so, they will not require any coordination. And that is the key, and that is possible because of any gossip-based cluster can have some properties which will enable this. To give the intuition of this kind of a data structure, set, the standard programming set is a nice metaphor. I mean here that if you have 3 nodes, and you are doing set operation, adding to the set operation on 3 different nodes concurrently, at some point they will have different information, right? I mean, as you can see here, each one of them have something else. But if you do a merge of these sets, in merge is a technical term, merge function for CRDTs, but intuitively here it will be union. If you do union of these sets, then you can see that yes, eventually all of them will have the same values, and it will be very safe operation. It doesn't matter which order you union or basically how many times you union, your values will be same. So this is one essential property, that if this merge function has this idempotent associative commutative property, then it can be used to have this kind of a data structure which doesn't require a lot of coordination. And the library that Akka ships with provides you with a set of such useful data structures. So you can just use it as a library on top of Akka cluster and get what you want. So how will I visualize how is the service discovery work? Assume that these are the 3 machines in the summit where our components are going to be deployed. We are already working in context of Akka cluster. So assume that these 3 boxes are forming a ring of Akka cluster. And on top of this, we can use CRDT library. And I'm calling this a copy of CRDT because CRDTs will replicate this data and make it consistent in such a way that eventually all the nodes will have all the information. But this data which is captured is a metadata. As you can see, it is a service information. So it's a meta, it's not going to be large. So it's perfectly fine if it gets replicated on all the machines. And then different components which are running on those machines can make a local call, right? It will not be over the network. It will be local service running, local host service running on the same machine, and get either register or get information. And that will be true for actor references, our components. That will also be true for any application that we are in control, like Akka HTTP service or any other service that we are writing, which also has a HTTP client, right? Even Python, for example, right? So the interface that location service will provide is a HTTP interface. So we can make our service register and discover other components. But we also want to use something like Redis, which we are going to start for our events, and register Redis coordinate with the same mechanism. But for that, we will require an agent. So we can write a JVM agent or some HTTP agent, which will register Redis on behalf. And that is a simple idea. And yeah, it worked very well, actually. I would say that that is the only mechanism for service discovery that we have. But it also has some challenges. Our requirement was to track as well as to list all the things which are registered at a given point. that required us to use two data structures, because there is no one data structure which will allow both the properties. So these are the technical names, LWW map and LWW register. There is because we are using two of them, and there is no atomic operation that you can do across the CRDTs, it is possible that while registering, you might go in an inconsistent state between the two data structures. And currently our approach is that if that happens, we give the error and ask user to retry. And with the retry, we eventually fix the problem. So that is one of the challenges, I would say. So yeah, that was about location service. I will briefly talk about the event service. So events are very important mechanism for both components to talk to each other, as well as publish their status continuously broadcast, so that it can be displayed or diagnosed for the functioning of the telescope. And what we are using for that is Redis, which is the backbone, the low latency backbone, where we are doing PubSub. We are using Lattice, which is the Java driver, Java reactive driver for Redis, and it is good. It is non-blocking, but it is slightly low-level API. And our domain, where we are using Akka Streams, which gives us nice streaming ways of composing subscriptions, that was not directly possible. I mean, we had to write some code. So we have written a small layer, a library called Romain on top of Lattice. And it's not a separate GitHub repository, but if you go to the CSW project in the TMT software organization, you will see on the top level folder Romain, which doesn't have any other dependency basically apart from Lattice and Akka Streams that we created, and we are using that for our event service Lattice. So now some numbers here. So what we wanted to achieve was that 99 percentile latency to be less than 5 milliseconds. And we achieved that for a traffic of around 40,000 events per second. These are very tiny events. And this is supported just by one Redis instance and the Romain wrapper. And in fact, if you look at the 50th percentile, it is less than 2 milliseconds. That is one of the highlights, I would say, that when we started, we are not sure we'll get these low numbers because we are in the JVM. Redis is really good, but we are in the JVM world, and we wanted to see that we don't add any overheads on top. And yeah, in the end, it worked out. The next bit is about the ESW or operations modules that Purva talked about. And there are lots of things here, out of which I'm going to talk of a DSL, scripting DSL. So in the control system, sequencer and sequencing is a terminology. I mean, we also learned it. It's a very common terminology where there is a higher level basically instruction set, which is used by the operators which control the system, and they orchestrate different parts. They say that, okay, first do this and then do this and subscribe to some events and so on. And there are some industry adopted versions. There is one system called Epix, which is very popular in this domain, but it is completely different technology. So it doesn't match well with what we have here. So instead, what we did was created our own DSL. It's an embedded DSL. We did not write a full-fledged language, but created an embedded DSL within a language. Initially, we started with Scala because Scala, people say it's great for embedded DSL, and it worked well. But there were some issues with the syntax, which we did not like. And I'll tell you what were those, and that's why we moved to Kotlin. It was even better. So our current embedded DSL is in Kotlin, but that also forced us to. So we have lots of repositories already because of this various modules, and we don't necessarily try to create small repos further just to keep it sane. We have, for example, one repository for CSW, one for ESW, and so on. But now in that one repository, you have Java, you have Scala, and you have Kotlin, both basically. And we want to support this using the same build tool that we have, SBT. And there was no direct way to do that. So we had to write a SBT plugin, a plugin for a build system, SBT Kotlin, basically. Pritam wrote that, most of it. That was required for us to support this basically thing. How does this DSL look? So this is using the basically Kotlin script syntax. So script is basically a block where you have some details. The important thing is that all these scripts will be very stateful. They will have state which will get updated once you receive some command or once you receive some event, and those commands and events will be concurrent. I mean, we don't have any control when the multiple events will hit the script. So essentially we are talking of handling a mutable state in a concurrent setup, and also providing a DSL where user is not aware of the concurrency, because first of all, we are saying that this is a higher level DSL. These are not the programmers, these are the operators, and we should give them something simpler. But at the same time, we have to deal with these concerns for real. And one of the things that we did for that is basically this is the problem, again describing the same problem, that the multiple concurrent accesses to the shared mutable state. What we did was we ran every script will be run on a single thread. But if you do that, then for things to happen concurrently, we have to ensure that everything is non-blocking. All the things are non-blocking. But the moment we bring something non-blocking, we have to also ensure that it is easy to use, because if something is async API and user will have to use async await or flat maps and stuff like that, that will not be acceptable for the DSL users. And I think that is where Kotlin helped us, and Scala failed us to some extent. I would say that however much we tried, Scala leaked those details, like we had to use async keyword at multiple places, and then if you forget that, then there will be the unexpected side effects. While Kotlin allowed us, because Kotlin's asynchronous function are marked with a keyword suspend, and that can be hidden in the implementation. User can still code in a imperative style without realizing that when the delay call is happening here, actually it's a async call and it is going to get suspended. That can be hidden. That was not possible with just a plain Scala DSL. Another thing where Kotlin helped us is like this red thing that we are demoing, that because of this context functions, we can enforce what kind of a DSL part is available within a particular scope. So for example, within a loop, move motor is not allowed by the syntax, and that can be easily enforced in Kotlin, and that was a good win. So yeah, that was the story about the scripts and the scripting DSL. Next, I will talk about the telemetry archival or the data side. So data service is going to eventually deal with both telemetry as well as science data, but currently we are focusing on the telemetry data, and that too, this is a prototype. This will then iterate into actually production implementation, but right now we're just trying out things. So here, very briefly, right now what we are prototyping is some simple queries against known data, right? So we are going to have 1,000 odd different event types which will fire at different rates. And if you compute the total size of the possible data collected every night or daily in that terms, it will be around 300 gigabytes. And yearly it will be 110 TB. So that is a lot of data. The data is not very heterogeneous. I mean, all events, and within events, of course, they will have different details and all that. But yeah, that is it's a temporal event data, almost a time series data that we have, but it's a large data, and we cannot use a traditional solution like Postgres is our default choice everywhere, and we cannot use something like that. So we have to think of a big data system where files can be split across multiple machines and stored. And then we also want to support, for example, simple queries like retrieve temperature, moisture from this data between this timestamp and that timestamp, that kind of a thing. And those queries should run reasonably fast. That was the objective. So what we have decided to do right now, and we measured, and it's working good. And I thought we should share this, because this is also, we are adopting some of the latest things we are hearing in the industry, and they make a lot of sense. Lakehouse is the term which is being coined. It's a half marketing, half tech term, where some of the goodness of data warehousing is being basically like superimposed with the data lake, where you just dump everything into HDFS or object store. And this goodness of data warehousing, mainly in terms of transactions, not across tables, but at least within a table. If you're doing a transaction, you get that support. And we were not so much interested in the transaction part, but it also gives us some interesting things, and I will describe that. So let's see what happens in this pipeline for the Lakehouse architecture. That we subscribe on the summit, we subscribe to all the events coming from Redis. And that is the ingester job, which can run on multiple machines actually. And every 2 seconds, it will write a JSON file of a few thousand events. And then every 5 minutes, we will run a Spark job, which will pick up these JSON files and basically convert them into Delta format, which is nothing but Parquet files and some extra metadata, and dump it into HDFS. So our store essentially is HDFS in Summit local, in the base facility near the Summit, and the format is the Delta format. The one good thing about this is, as we are trying to minimize the infrastructure that we deploy for doing different services. One will naturally think that if you want to, in such a situation, if you want to write a lot of streaming jobs, like we had to, for example, we have to periodically run a compaction job, which will compact these small files that get generated because of the streaming nature, like few MB files that get generated. We want to compact them into large files so that we don't degrade the performance of our storage. And then eventually we'll have to run a periodic job to migrate this data from the storage to the object storage. And these are just 2 samples, but there will be other jobs we expect to happen. One would naturally think that Kafka-like streaming system will be very nice, because it will allow you to publish on a topic and listen to it, and then it will Spark in combination with Kafka will allow you this fault tolerance, and then if you restart, you know from where to start, and so on. And it will also give you decent latency. In this big data world, achieving good latency is not easy. It will give you very good latency. But for the archival purpose, we don't have such a big need for a low latency. We are fine to have a latency of few seconds or even few minutes, basically. What Delta allows us to do is treat each table, because Delta table essentially is keeping those transaction records. It allows you to treat each table as a messaging queue, and that is what is the win for us. So each table can act as a message queue, and writing streaming pipelines just on these tables without any external messaging queue is possible. It's in fact very trivial. And that was a good win. And it also uses columnar structure to store the data, so the queries are efficient. But that is not the only reason queries are efficient. We have to make few decisions for each type of query. We have to make such decisions. That is part of how the big data has to be dealt with. So we partition it accordingly. We partition it by date and event name, because most of the queries are going to be fired against a particular date and a particular event name. And then within that partition, which is going to be from 1 to 10 GB, we keep it ordered so that when Parquet files are split into row groups or different HDFS blocks, each block always have the contiguous time series data. And this ensures that even if we accumulate terabyte of data, it doesn't matter, because our queries are very simple. I mean, our queries are going to mostly ask for 1 hour, 1 minute, or 1 second basically duration, and we say that, okay, within span of that duration, give me project some information. And if you arrange it in this format, then we can almost ensure that we scan hardly just one block. So even if we have one single core to process this information, it will be possible to solve these queries within few seconds. And maybe in some cases we may have to use more cores and scan more blocks, but that is working well so far. So yeah, that was about data. I'm going to move to the engineering UI, and then yeah. So we have like 30 more minutes. Is that right, Jina?
20, 25?
25.
okay?
Okay, so I'll
Yeah.
maybe, yeah, I'll stop. Hopefully in 10 minutes, I should stop 10 to 15 minutes, and then we can have some Q&A.
Okay, awesome. Thank you.
So for the engineering UI, which we recently started working on, by the way, the interesting part of this project is that the same team is working as a team of 10 people working on all whatever comes our way, right? I mean, it's like a backend services, user UI applications, big data systems, and so on. So that is interesting, and that is good. So we are. I'm myself new to the web, and I was our customer is not familiar with the web, how web applications work. I mean, in their world, swing application and thick applications are the norm. And we convince them that no, I mean, we don't do that these days. These days, browser is the most powerful delivery mechanism, and it's very capable. So that was one battle. But after that, we ourselves, I mean, I found this web to be very confusing, to be honest. Some decisions were natural and easy for us. One is that TypeScript. People like it or hate it, but we like it. We come from Scala and that background, so we like types. We also don't have much requirement about what kind of a branding or marketing personality our applications will have. So we are okay to basically have any consistent look and feel for many of our applications. So we are going to make use of some component library like and design system component library, which gives us a lot of things off the shelf. And we realize that React is the standard. We also realize web components and other things are really basically the thing to go. But the ecosystem is such that if you look at and design system, which is very rich, that we wanted to adopt, and see that what kind of a component it provides, by default it provides React components. There's some third-party support for other systems, but we didn't want to rely on that. So React became the choice because of that, and React and React related tools, which I will not talk about. So those are some usual suspects. What we are trying to do is adopting ES modules, coming new to the web and trying to use the ideas that we are very familiar in JVM or any other world where we can package modules and then use them as different packages. We realize that if once we adopt into React and Webpack, that completely breaks. I mean, Webpack just bundles everything together and then pushes it in the application as a script. And then if you have to split, you have to do a lot of work for that. But we also learned that browser supports module system for a long time, but apparently it is not popular for whatever reason. And then we learned the reason later on, that to be able to make use of that module system, you have to have a build system which is compatible. So Webpack is definitely not, Webpack's focus is definitely not ES modules. And you have to have a test runner or a testing ecosystem which is also compatible, and Jest, which is the most popular one, also doesn't care much about ES modules. I mean, they are adding support now, but it doesn't work very smoothly. So we had to basically look and search for these tools. So we settled with Snowpack and Web Test Runner. Web Test Runner is very, very recent, and that saved us basically. Otherwise, we would have just given up on ES modules and gone back to a traditional way of bundling everything. And that is what we have adopted. So just sharing that, maybe some of you will be UI into UI, and you might benefit from that. This is one very early prototype we did. This is not real, just prototype, but it's very popular. So we are showing that. This is depicting the hexagon honeycomb and the streaming events which are coming to the browser to tell where the faults randomly, and then we are just displaying. Hopefully the faults won't happen so often, but yeah, these are the kind of interfaces that we look forward to. Currently, we are building the control system UI. I have a click through for that on my machine, but maybe if time permits, I can show you that. but right now I will stop for the UI here. Okay, so I think we talked about a lot of these things already. Tech stack. I'll just highlight the things which are unique and which we did not speak about. So Borer is a Scala library, which is I'm like very happy with. So we have adopted one library. So we are a closed ecosystem, right? In a way, we are all JVM in Scala, and then very minimal support for like a outside that. So we have adopted Borer as our serialization library, and it is very nice because it is very efficient. First of all, it goes from the Scala case classes to your representation without any intermediate AST creation, which is nice. But most important that it supports both CBOR as well as JSON. So CBOR is a binary representation and JSON is a textual representation. So our JSON is the main representation when it comes to the web interface, but CBOR is what is required when we talk between the different actors, and CBOR is what we use to encode messages or events when they are published onto Redis. And then this allowed us to basically unify all that. So our set of domain models just use one set of codecs, and they work everywhere. They work for CBOR as well as for binary as well as text, and Akka, Redis as well as HTTP. So we are very happy. In fact, I have gone ahead and created a small library called msocket, which makes use of this and abstract a few other things to allow easily write web services from a Java or a Scala API. So you write a Scala API and you want to serve it without having to use gRPC or any code generation framework. You want to basically enable a HTTP endpoint or some other protocol like WebSocket endpoint, or even RSocket for that matter. Using this encoding, it is possible, and we are msocket with HTTP and WebSocket is being used across our services. msocket is also, if you search for msocket on the software organization, you will see that it's a very nice project. So that is one interesting bit. The Coursier and Jetpack, right? This is also very new, very interesting, and it's very useful for anyone who is onto the JVM ecosystem, but not many people know about it. So Jetpack allows you to, we have binary dependencies in our ecosystem where one project depends on the other project's binaries. We are creating like a Spring Boot set of multiple projects and publishing them for the SCD writers. And because we are that kind of a project, we do need to depend on our own binaries. Every time doing through the publish cycle, publishing it on Maven Central and consuming it from there like a snapshot or otherwise, it's a time-consuming process. And Jetpack actually solves that beautifully. I mean, you should have a look if you're into JVM and have similar requirement. Just look at Jetpack. You will figure it out what it does. It is not a source level dependency. It is a binary dependency mechanism. You can use your existing tools like Maven and Gradle and SBT, but it allows you to have quick dependency during a development cycle, quick dependency within your libraries. And Coursier is like, you might have heard of SDKman, which allows you to install applications, command line application stuff. Coursier is like a very basically very powerful version of that. So on a given machine where you just have nothing, basically command line, from Bash to all the way to installing JVM to versions of Scala to our own applications, not only installing but launching. So for example, if we have a CLI utility for monitoring events, I can launch that just from a clean machine, a machine which doesn't even have JVM. I can automate things by installing the JVM and then all other applications. So Coursier in combination with Jetpack has become the backbone of our day-to-day development. And in fact, that also enables the agent service that we talked about, which is also Kubernetes-like thing where if we know that the agent is running on one particular machine, we can remotely ask to basically provision certain things on that machine, which does not exist on that machine, but it will be downloaded from internet and installed. So those are the things. Right. So Yeah, these are some of the open source contribution. MSocket I talked about, Roman I talked about. Embedded Keycloak is a small testing library where you can embed Keycloak for testing, auth API testings. We have two SBT plugins. One is for documentation and one is for Kotlin, which is all open. There are a lot of unique things about TMT. We try to cover. According to us, it's pretty modern tech stack we are going after. It's a very interesting domain. All the work is open source. And there is ongoing maintenance. Every time we build something new, by then we are 4 years into the project already. It's time to basically go back and change few things. People who start consuming our stuff, they continuously keep reporting things which are not working in certain ways. So that is ongoing. And yeah, we are going to be involved for 10 years, but we expect to support it for 50 years. So let's see how it goes. But that's also interesting aspect. Another interesting aspect is requirement translation. The lingo used by the Telescope people and the business software is different, and we struggle to translate that. There's no immediate consumer once we do our release. Like once you release Spring Boot 2.4, I mean, there will be next day people will be downloading and using it. For us, we have to wait a good amount of time and convince people saying that, okay, now this is new, please go ahead and use that. And so our feedback cycle is also slow, I would say. Waterfall, merging our philosophy of iterative development with waterfall is another challenge. Educating tech stakeholders about modern tech stack is also a challenge. I mean, those are techies, they are into software, but they understand software slightly differently than how we do. And this is a continuous task for us to basically keep them filling with what we feel is the right choice and going forward. So those are some of the things. This is the team. Me and Purva spoke. Chaya is here, and then all others are also here. They have TMT in their name if you want to talk to them. Yeah, another photo. This is a huge list. So there's 3 teams, one in Pune, one in Pasadena, and one in Bangalore working. And these are all the active projects that we are contributing. And there are a lot more within the organization, TMT software organization, that you can have a look at. So I think that's it. Thank you. I'll be happy to take questions. Yeah.
Wonderful. Thank you so much. You know what? The TMT has been on top of the chat and has been answering all the questions. So right now, everything I would say is covered. I don't know if I've missed something that's come up very recently. So if anyone does have questions they'd love to ask, please put them in the chat now. And if anyone from the team wants to say something too, they're of course very welcome to do that.
So Mushtaq, there was a question around, did we consider Databricks for data side?
Yeah, actually this is a prototype, and we quickly realized that Databricks is a very nice way of adopting this technology. I mean, if we have to maintain our own Delta, we'll do some work, but we will not get the same performance, because if you read all their papers, right, all their open source tools are a trick for you to buy into their commercial product, because they're significantly better, and they're also cloud based, and that could simplify some of our workflows, and we don't have to maybe maintain anything in the base facility and directly keep on the summit. So that was very attractive, but the architect is not comfortable with that approach. So we are okay with basically some object storage in future in AWS, but for the 6 month or 1 year data, we want to be in the summit, and we want to fully control it, and we don't want to buy into anything which looks opaque, a little opaque to our architect. So in fact, he was very uncomfortable that we are using something on top of Sparky. So he was very fine that, okay, use Sparky files, use Spark, or maybe if Spark is not there, we'll use some other way of communicating. But what is Delta, and why are you even considering that? And we had to convince him that, okay, no, this is still open source, and this is a small layer, and Delta supports you to read, supports a standalone reader, which is JVM based and which does not require Spark. So it's an open system. So because of those concerns, we have not gone ahead with Databricks, but yeah, we are aware of it. And in fact, I would say that if this works for us, then Databricks will be a good option to consider. Yeah, I think Yeah, feel free to ask. I am not able to scan it fast, but if someone asks to audio, you want to unmute and ask, that is fine too. Yeah.
All right. And I just want to mention too, while we're waiting for questions to come in, that this is a series. We still have 5 more sessions to go. I'm going to ping those in the chat and maybe in a few more minutes show the upcoming sessions in the slide. And as Mushtaq said, if anyone wants to unmute themselves, please go ahead. And yeah.
Yeah, I see some FITS discussion happening there. So FITS header, I will just say what I understood from there, that FITS is the header, and it's right. It's going to be header of the image, which is actually science image, which is not the meta. But to create the headers, we need the metadata. So the work that we are doing in metadata collection is basically listening to all the events basically which happened during that exposure, and using that information to construct, using a FITS a formatting file, construct a FITS header, which can then directly sit on top of the science data frame, which with the observation data, as someone pointed out. So yeah, they're interlinked. Pritam, Purva, anything else is of interest? I mean, we should.
There is one question on chat just now, like, are you considering AI or ML processing at this time?
Right. I think we tried to make an effort in the presentation to say that, okay, we're still dealing with telemetry data mainly. Yeah. Science data will also come where it will be large images. It won't be as large as radio telescopes. So the really big challenges which radio telescopes like SCA throws at you, I mean, those won't be applicable for optical telescope, but there still will be large images. Maybe every exposure will be few GBs at least, right? And there will be some requirement for some basic processing using the tools, ML tools, but that will come much later. I mean, right now we are not into that. I mean, that is not even in the scope of the work that we are doing right now.
I see a question from David. How are you testing your software packages? I understand that the telescope's hardware is not yet there, but do you have simulators for all devices and components?
Pritam and Pura, you are better in answering this.
So yeah, I was just trying to type it, but I will say that we don't have simulators for hardware components, but what we do is like we have shown the layered architecture. So we mock at HCD layer, which is like the layer just above observatory hardware. So we mock at that layer, and from that layer above we have all the unit testing, integration testing in place. Pritam, would you like to add anything?
Yeah, that is correct. So we actually don't deal with hardware directly. So we have simulated FCDs and assemblies. So though they just simulate that if if we send some command to that hardware, it returns you some fixed response. So we simulate that in the software itself, and eventually there will be an environment at client side where there will be a simulators, and they call it still setup. And eventually we have some test, and eventually we are going to write some test which will run in those environments, but that is not in place as of now.
Wonderful, thank you. Any last words from the TMT team as the session starts to come to a close? Or insights into what to expect for the upcoming series too?
Yeah, thank you for the opportunity to share about TMT project. I mean, if people are interested in the TMT specifically, I mean, send across. My email is mushtaq@thoughtworks. So ping me, I'll be happy to answer the questions. Chaya is the person who looks after the overall E4R. So I will let her answer what is coming next. Yeah.
Wonderful. Would you mind
Thank
sharing?
you.
Oh,
yes,
perfect. Thank you.
Yes.
No worries, no worries. So just a heads up to the next E4R session. It's going to be on life sciences and on automated drug discovery. So that's another feature that we are coming up I think that's next week, I guess, April 8th, probably. So looking forward to all of you being there as well. Thank you.
Thanks so much, Chaya. And here is an overview of what to expect between now and July. Cool. Thanks so much, everyone. Fantastic job. Thank you so much to the team and for everyone for joining.
Thank you.
Thank you.
Thank you.
Thank you. Bye-bye.